Hello, we are ready to go. I start the live streaming. Thank you, everyone.
Okay. Hello, everyone, and welcome to the fourth workshop on testing analysis and application of cyber physical system and Internet of Things. This workshop is co-located with ISSTA 2020. This workshop was organized by Professor Xin Yu from the University of Kentucky and Professor Yang Kai from the Institute of Software Chinese Academy of the Sciences. My name is Valerio Terragni from the Università di Svizzera Italiana in Lugano, Switzerland. I will be the chair of this workshop, and I served as a P member since the first edition in 2018. Today we have an exciting program. We start with a keynote by Lionel on artificial intelligence for automated software testing in cyber physical system. And then we'll have two talks because the last talk it cannot be done today, so we have only two talk which are two invited papers. And then I invite all the speakers to join the panel discussion in the last hour of the workshop. So after the fourth talk, we will have a 15 minutes break. So if you have a question during the talks, you can write the question on the Zoom chat or in the Slack channel. Okay, let me introduce Professor Brand. So first of all, we are honored for your acceptance of giving this keynote. And Lionel Briand is a professor of software engineering and has shared appointments between the School of Electrical Engineering and Computer Science at the University of Ottawa in Canada, and also at the S&T Center for Security, Reliability and Trust at the University of Luxembourg. He is the head of the Software Verification and Validation Lab at the S&T Center, and he is a Canada Research Chair in Intelligent Software Dependability and Compilance. He holds an ERC Advanced Grant, the most prestigious European Individual Research Award, on the topic of modeling and testing cyber physical systems. He has conducted applied research in collaboration with the industry for more than 25 years, including the projects in the automotive, aerospace, manufacturing, financial, and energy domains. Lionel became IEEE Fellow in 2010 for his work on testing object-oriented system, and he was granted the IEEE Computer Society Harlan Mills Award in 2012 and the IEEE Reliability Society Engineering of the Year Award in 2013 for his work on model-based verification and testing. So without further ado, please, the stage is yours. Thank you.
Hello. Good afternoon actually from Montreal in Canada. That's where I am right now. I would like to thank, of course, the organizers for their kind invitation. Let me try to share my screen and see how this works. All right, so if I do this. All right, can you see my slides in the right mode? Hello? Hello?
Yes, yes.
Lionel, it's fine. I can see your slides, no problem.
Thank you.
All right. Well, I was not sure if you heard me. Okay, all right. Well, anyway, good afternoon, and thank you again.
Good afternoon.
So, well, the goal of this talk is to report on personal experiences regarding the use of AI techniques in automating the test of cyber-physical systems. Obviously, given time constraints, I will only provide a partial view of the problem, but I will try to draw general lessons learned and provide pointers for further information through references. Everything all the examples I'm going to give are actually research projects that were run in collaboration with industry partners, and not just academic exercises. A disclaimer is that I'm not going to try to provide a survey of the field, obviously not. I'm only reporting on personal experiences, which is inevitably biased. So, having said that, I want also to acknowledge all my colleagues, postdocs, and students who have been working on the projects that I will be presenting as examples. So we all know what cyber-physical systems are, otherwise we would not attend this workshop, but here is a definition: a system of collaborating computational elements controlling physical entities. And what characterizes our systems is that they are increasingly autonomous. They are increasingly machine learning based, for example, based on deep neural networks, especially in the perception layers. They don't just provide recommendation most of the time, they actually act on the physical environment, and therefore there are safety implications. And actually many of those systems have to comply with safety standards. The development process of such systems is different in some ways than other types of systems. What I have here on that slide is an oversimplification, but still it conveys the main point, which is that the process is divided into three phases: model in the loop, software in the loop, and hardware in the loop. In the model in the loop stage, everything is a functional model. The controllers, the environment or the plant, the decision algorithms. So for example, those models can be continuous and discrete Simulink models, which is the case in, 90% of the cases. And then eventually, the controllers, the decision algorithms are transformed into actual software that can run on the deployment platform, but the environment is still simulated, and this is a software in the loop stage. And eventually, we move to the hardware in the loop stage, where the environment is not simulated anymore, or not completely, or it's an analog. Those are analog simulators of certain hardware pieces, but the system is actually executed on, in a realistic environment. And when we talk about testing, obviously, testing is much cheaper in the model in the loop stage than in the hardware in the loop stage. And software in the loop testing is somehow in between. Usually people try to find as many problems as possible in the control algorithm, in the decision algorithms, in the model in the loop stage, so that when they move to the software in the loop stage, those algorithms are, as far as possible, correct. Then, of course, there is more software being developed in the CL stage. The rest of the system, basically, beyond control algorithms and decision algorithms. And usually in the CL stage, you have new forms of testing that you could not perform before that focus, for example, on performance aspects. But I'll get back to that. All right. So in the mill and seal testing stages, one of the main challenges is that it's very computationally expensive because we are simulating physics models. And that means that every test execution is very expensive. In the yield stage, the bottleneck is more the human effort involved. You know, for example, in setting up the hardware and analog simulators to be able to execute every test case. But in general, regardless of the stage you are at, test executions tend to be limited compared to other types of systems, like, I don't know, testing a web system, for example. You cannot just run the thousands and hundreds of thousands of test cases. I mean, that's usually not possible. The problem, of course, is that the test input space is very large and is determined, of course, by the complexity of the physical environment. And inputs usually are signals, and not just input values in such systems. But because those systems are safety critical, very often safety standards require that there is traceability between system testing and requirements, so that the system can be certified and deployed. So as you can see, I mean, this, just by looking at the slide, you can get an idea of what the challenge is here, or the specific challenges regarding cyber physical systems. So in the title of my talk, I have artificial intelligence. Obviously, that phrase doesn't mean much. So what I mean by that is the use of three main types of techniques: meta-heuristic search, machine learning, and natural language processing. And we'll see what role they can play. So let's start with mill testing, which is actually the type of testing where I spend most of my time. A first example of a project that was run with Delphi Automotive Systems was the automated testing of Simulink models. So everybody probably here knows what a Simulink model or a Stateflow model is. It's a data flow driven block diagram language. And you can actually execute and simulate Simulink models. And obviously, during mill testing, they must be tested. For example, you must test your controllers. The challenge in testing such Simulink models is that they are mixed discrete continuous. They have mixed discrete continuous behavior. So it's a combination of algorithms and continuous dynamics. The input and output are signals, that is functions over time. Usually they are configurable and they need to operate for a large number of configurations. Also, usually developing oracles is challenging because you need to somehow decide what is an expected or correct output signal. And usually there is some degree of uncertainty and some degree of tolerance. I mean, it's not an exact signal that you expect. So I'm not going to address all those problems today, but some of them. There are existing commercial tools such as RTES or SLDV verifier, but very often they are incompatible with many type of constructs in the Simulink models, such as time-continuous block, floating points, and non-algebraic computations. There are also scalability issues, and as we have seen in many of our experiments, they actually have a low fault revealing ability due to unrealistic assumptions. Very often, they expect the engineer to provide assertions, for example, to be checked. If I'm going to take the example of testing controllers, there are different type of controllers. You have closed-loop controllers, and you have open-loop controllers. I'll just use the latter as an example, but we have done work on both, as you can see in the references. So the problem with open-loop controllers as opposed to closed-loop controllers is that there is no feedback loop. So as a result, the output signals have to be checked manually. You cannot compare with what you expected. As a result, what we need, because the oracle is manual, we need small fault-revealing test suites. We cannot have very large test suites. So the challenge is in selecting the right test cases. And also, it's not because you cover an incorrect block in the Simulink model that you are going to be able to manually identify that there is a failure. What you need is that you need the observed output signal to be significantly different than what the engineer would expect. So we have, I'm not going to go into details, but we have an approach which is based on meta-heuristic search, and that tries to maximize output diversity and identify anti-patterns in the output signals. And by what I mean by anti-patterns, here are two examples, is they try to search the input space in order to generate output signals that are very unstable or that present very sharp discontinuities. So here you can see, abstract examples of signals with instability and discontinuity. And none of those things normally should be present in output signals and controllers, because they would, for example, damage the hardware. So by diversity, we mean, as you can see here, for example, vector-based diversity between signals. But we can also have more complex definition of diversity, such as features in the output signals that are based on the derivatives or the second derivatives that are observed in the output signals. But the basic idea is that by maximizing the diversity of output signals, we are more likely to find the type of failures we're looking for in our control, in our open loop control. And actually, that's what our experiments demonstrate, though I will not be presenting results here. All right, I guess this is just a conclusion of what I've already just said. But our results also show that our strategy outperforms existing commercial tools, such as RTES or SLDV, that I've briefly mentioned before. Another example of mill testing is in the context of testing advanced driving assistance systems. So here we are at a higher level, not just testing a controller or a decision algorithm. And you know what advanced driving assistance systems are. There are many kinds. They tend in general to be safety critical. They all have a similar architecture. They have basically control and decision components. They get data from car sensors and from cameras, and they control various actuators such as the throttle, the brake, and other things. And then the question, of course, is how to test such systems. There are challenges that are summarized here. You have a highly varied, environments. For example, road topology, weather conditions, building and pedestrians in the field of view of the car or on the side of the road. You have a huge number of possible scenarios in terms of the trajectories of cars and pedestrians. They play, of course, a critical role, and they have to increasingly satisfy various functional safety standards. So obviously, it's a challenge for testing. And of course, you can do on-road testing, but it's time-consuming, expensive, and unsafe. So usually before you do on-road testing, usually you do simulation-based testing where you have a physics-based simulator. And here is an example of a simulator I've used in the past called PreScan, a commercial simulator sold by Siemens. And when you test based on such simulator, you have the ADAS that we are testing that interfaces with a simulator which is based on a physical plant model where also other cars are models, pedestrian, and the environment. And the test inputs are basically simulator configurations where you provide the data about what are the different cars on the roads, their trajectories, the pedestrians. I mean, you basically configure the simulator. And as an output, you get a timestamp output of what is the positions of the various cars and pedestrians at every point in time, of course in a discrete fashion, and whether there are collisions, for example. So our approach to testing, as you can imagine, we cannot do any form of exhaustive testing, and random testing is unlikely to help us. And actually, that's what empirical results actually show. So we have a technique which basically is based on a mix of meta-heuristic search, and in particular, we use multi-objective genetic algorithm called NSGA2 that tries to somehow generate new simulation scenarios by optimizing some of fitness functions. Of course, I don't have the time to go into details, but for example, one fitness function could be about how close you are at any point in time from a pedestrian. For example, for an emergency braking system. So it tries to optimize the number of fitness functions in order to trigger safety violations. But it's not good enough in order to effectively search the input space. It also makes use of machine learning. In particular, for example, decision trees and other techniques that try to partition the input space into homogeneous regions in terms of the percentage of critical scenarios we observe. For example, in critical scenarios, maybe near collisions with a pedestrian or collisions, for example. And I don't have the time to go into detail, but at a high level, let's assume this is the input space. Of course, it's an abstract representation. We try to, we generate random scenarios. We compute their fitness, that is how close they are to trigger a safety violation. Based on their fitness, we classify, that is, we partition the input space to understand what are the parts of the input space that are critical in terms of safety violations. We then breed these solutions in that part of the input space in order to generate more critical scenarios. And we keep iterating. And then what happens is that little by little, we focus our search on the more critical parts of the input space. So here is a summary of our technique. It's basically a form of search guided by classification, machine learning-based classification. And what we hope to get in input are test cases revealing worst-case system behaviors. For example, worst case in terms of safety violations. And also a characterization of critical input regions. Help the engineers understand what part of the inputs are critical so that they can understand whether this is due to limitation in the hardware or whether there are problems with their control and decision algorithms, for example, in those parts of the input space. Of course, the problem as I've presented it is a simplification. In practice, it's more complicated because you don't run one ADAS, you run concurrently several ADAS who actually send commands to common actuators, whether the steering, the acceleration, or the braking, for example. So that means you can have interactions between those ADAS systems or those autonomous features, which may lead to safety violations, though individual ADAS systems are safe. And of course, that's a much more complicated problem that we have also addressed in some publications that are in the references of my slides. And I don't have the time to go further into details, but I just wanted to tell you that, of course, the problem in practice is more complicated because of interactions between ADAS systems. There are, in general, when you are testing such Simulink models during meal, there are general problems of scalability and oracles. I've touched upon that, but let me revisit the problem. First, very often you want to check the outputs in an online mode. You don't want to run the entire test case and then analyze whether or not there was a violation. You want to stop the test case execution when you find a violation. And the reason is what I've said, is because those Simulink models tend to be compute intensive. And we have a lot of examples where it takes a long time. For example, to execute a test scenario for a satellite in orbit may take 1 hour, 1 hour and a half. Also, as I said before, test oracles should be able to handle uncertainties in the model, because often sensors provide signals with noise. You have parameters, you don't know exactly what sensors and sensors you will be necessarily using in the future. And there is some uncertainty regarding various parameters, for example, at the middle stage. All right. And so just briefly, we have developed techniques for dealing with such online oracles, where we have functional requirements into a restricted signal first order logic, restricted so that the generation of online oracles is possible, and at the same time we can express all the type of properties that we need in such systems. Then we have a way to automatically generate oracles and automatically check online oracles accounting for uncertainty. So that's how we basically solved that problem. But that doesn't solve the entire problem. Sometimes models are so long to execute that we cannot test, we cannot simulate a model for every test case. So, and testing by definition is going to require a lot of executions. So what do we do when we are dealing with compute-intensive CPS models? Well, we have developed a technique called ISSTA based on system identification and interactive refinement. And I won't go through the detail, but I'll give you a high-level view. So basically the steps is that we use what's called system identifications, that we'll be using Matlab libraries, in order to build surrogate models of our models. And we then test the models, the surrogate model. If we find a problem using falsification techniques, such as ISSTA, for example, then we check whether or not it's a spurious failure due to the approximation of the surrogate model or a real failure. If it's a surrogate model, if it's a spurious failure, we have an iterative refinement strategy until we don't get spurious failures. And we have, of course, done a lot of case studies using ISSTA, and we have shown that this actually is much more efficient than testing with the original model. Last problem is that very often properties or requirements are only true under certain assumptions. And often those assumptions are not documented. So you know that your Simulink model is based on a number of assumptions, but it's not documented. So we devised the technique using machine learning and genetic programming to automatically learn such assumptions. And again, I'm not going to go into details. You can check the paper if you're interested. We basically have smart sampling techniques in order to decide what test cases to run. Again, always for the same reason, to minimize the cost of testing when you have complex models. And we use machine learning, or we have two approaches, or genetic programming, to try to learn assumptions that somehow fit as well as possible the data in an iterative fashion. And then we iterate until we have satisfactory assumptions or accurate assumptions. And assumptions also that are as informative as possible. All right, so this was an overview of nil testing. Let me check the time, yes. So now let's move on to seal testing. I'll be shorter on seal testing. because it's a little bit more standard for software engineers. But still, there are specific problems, and let me give you an example. Usually, as I told you earlier, still testing is the place where you start doing performance or stress testing, because you cannot do that before, obviously, because you don't have the platform. You don't run test cases on the deployment platform. So here's an example with Kongsberg, sorry, in the energy domain. All right. So, as you know, in many of those systems, you have concurrent independent tasks. Tasks have deadlines, with respect to the arrival time of the events that trigger the execution. For certain critical tasks, those deadlines are very important and are very critical. The task properties depend on the environment or are design choices. For example, priorities are design choices, and their worst case execution time depends on the environment. Tasks can trigger other tasks or share computational resources, therefore they have interdependencies. And this is the case, for example, of a project where I worked with Kongsberg, where they had safety critical driver tasks, or drivers for the hardware that the system was controlling. It was a system monitoring gas leaks and fire in oil extraction platforms. That's where that activity, how that activity started. And of course, there is a whole field called scalability analysis, which is based on, mathematics, a certain type of mathematics, and that tell you whether a task is schedulable or not, based on a number of assumptions, such as estimates of worst case execution times. However, scalability analysis is not good enough because it usually is based on many assumptions, and not just the WCET assumptions, but also other assumptions. And in addition, you don't just want to know whether a task is scheduled or not. You want also to know, because of those assumptions, how close you are to possibly violating a deadline. So eventually, anyway, you need to generate stress test cases that are going to maximize the chances, for example, of missing a deadline. And usually that type of testing is expensive because, for example, you have hardware in the loop or various other reasons. And at the same time, finding stress test cases is difficult. And why is that difficult? Because, for example, whether a task meets its deadline, so for example, J1 here, depend on the arrival time of another task, due, for example, to preemption. And because of all the interdependencies, between tasks, the fact that they can trigger each other, that they can share resources, that there is preemption, it's not obvious to know what are the test cases, for example, in terms of arrival times, that are more likely to trigger deadline misses. And again, the problem we have here is that the input space is very large. You can imagine the size of the input space in terms of the arrival time of all the tasks when you have many tasks. Also, parts of the input space is infeasible because of interdependencies. So what we did is that we re-expressed the problem as a constraint optimization problem, relying both on, and I'll explain it to you intuitively in the next slide, constraint programming and meta-heuristic search, or genetic algorithms. And the reason why we combine those two is because those two techniques have interesting properties that are complementary. Genetic algorithms are scalable, and CP offer guarantees. So what we did is that we combine those two techniques by using first genetic algorithms to explore efficiently the input space. And when we found worst case scenarios, here represented by the circles, we then explore the neighborhood of those scenarios using constraint programming, and therefore getting guarantees about what was the worst case scenario within that neighborhood. And we found very interesting results showing that the combination of those two techniques was much better than those two techniques independently. And of course, much better than random search. And here is an overview of the solution. So we modeled the task architecture using the Marte profile of UML, and then in the first step. And then we use those techniques to generate stress test cases, that is test cases that maximize the chances of deadline misses. And we did the same thing, by the way, in another environment, in the satellite domain, more particularly in a satellite attitude determination and control system. Except that here we did something in addition. Engineers wanted us to learn what were safe WCET ranges. Safe according to a level of risk decided by the engineer. So we built on what we had done before in order to find an efficient way of doing this using machine learning. Hill testing, the last phase. So here is an example with another industry partner, also in the automotive domain. As you know, in many industries, requirements are expressed in natural language. And it's not going to change, even in safety critical systems. It's a practice that is never going to disappear and that will probably always remain very common. And usually those requirements have many stakeholders. That is, they are used as contracts, for example, among stakeholders. They are used by independent testing teams, acceptance testing teams, which even are geographically usually separated, etc. Or they may be shared by many companies on large projects that involve many companies, such as, it's typically the case for European Space Agency projects, for example. So they play a very important role. And they must be read by many different people, and that's why often they tend to be in some form of natural language. Well, it's true for example, many automotive embedded systems, for example, those developed by our partner, IE. And also, very often, those requirements tend to change. There is a constant negotiation that is taking place. It's not like they are defined when the project starts, it's that they keep changing and negotiations keep happening all the time. As I said before, and that's true here as well, traceability requirements and test cases are required by standards, customers, certifiers. And of course, you can imagine that you need to preserve that traceability. Often, a common practice is based on having the big traceability matrices, but it's completely impractical and very expensive. And there is academic work on using NLP, natural language processing, to automatically match requirements and test cases, but none of those techniques are sufficiently accurate, even after decades of research, to be used in practice. So our problem is that we need to automatically verify the compliance of software systems with our in the loop with their functional requirements in a cost-effective way. So what we decided to do is that instead of managing traceability or helping people manage traceability, we decided to see whether it was possible to generate system test cases for checking compliance with the requirements from requirements in natural language, and then have traceability as a byproduct. The problem, as you may guess, is that textual descriptions of requirements are often ambiguous, incomplete, and not analyzable automatically. So then what we try to do is to stick to natural language, because for reasons I have mentioned before, but also restrict its usage to make it amenable to natural language processing in such a way that we can use that for system testing purposes, and try to find the right trade-off. As usual, for many software engineering problems, we have to find the right trade-off between many things. So we use a technique, a use case modeling technique, and I'll tell you why, called Restricted Use Case Modeling, RUCM, which was published in TOSEM in 2013. And the reason is that that technique, first, our partner, like many people, tend to express requirements as use case specifications. Why? Because it's readable by a large number of stakeholders. And at the same time, it's sufficiently operational to provide enough guidance to developers. That technique is also, because we restrict the way use case specifications are written, is analyzable by natural language processing. And therefore, it can be a starting point to try to achieve our objective. So here is an example of system where we applied it, a system that tries to determine the occupancy of a car, especially when you have children and when you have bumps on the road and stuff like that, in order, for example, to decide whether the airbags are turned on or not. So I'm going to go into detail, obviously, but just to tell you that RUCM specifications, they look like use case specification, except that they use keywords that are in blue here, and that they restrict how you can write a sentence. And of course, we have an NLP-based editor that guides people into making sure that they comply with the RUCM rules. And those keywords are useful because they allow us to identify what are different types of steps: input steps, include steps, conditional steps, internal steps, output steps. And then once we know that, we can use NLP to identify, for example, domain entities, which are going to correspond to inputs and outputs of our system. And also constraints that we will have somehow to deal with if we want to generate test cases. Okay, here in natural language. So we usually analyze using NLP those use case specifications. We generate a test model that will support us in generating test cases. It's a form of graph, as you can see here. So a labeled graph. One problem, of course, is that our constraints are in natural language, as you can see at the bottom of the slide here. Let me hide this. Can I hide this? No. Okay. I won't go into details, but somehow we need to take that constraint in natural language and generate a constraint that can then be fed to a constraint solver. And that's the only way we can generate full test cases. Here, in our case, but it doesn't matter, we use the object constraint language as a constraint language. And actually, we built a dedicated constraint solver because the type of constraints you have in system specifications tend not to be solvable by typical solvers, such as SMT solvers. So we developed a dedicated solver that can be used for generating, for example, system test cases on the type of complex constraints that we have usually. And we developed a technique to do that is based on NLP, and more specifically a technique called semantic role labeling, or SRL here for the acronym. And it's a dedicated NLP technique that we were able to use to automatically go from natural language to a solvable constraint. So another example of hill testing is in-orbit testing in the satellite domain. And the reason why I'm just mentioning that briefly, there is a paper as well, is to show the diversity that hill testing can take depending on the domain and the context. Here you are testing a satellite in orbit. You have time constraints because there are only time windows where you can do that type of testing. You can damage a hardware. There is uncertainty in the environment. So just to give you an example, and somehow you have to help people decide within their time constraint and given all this, what test scenario they should execute in order to minimize the risk and maximize their chances of finding a problem, a critical problem. All right, so let me just reflect on a few challenges. So I've already told you about the challenges, here they are summarized very briefly. Model execution is expensive, you have hardware in the loop, input spaces are huge, and there are signals. Of course, failures may be critical. And standard verification approaches have severe limitations in that context. I don't have the time to go through that, but you have seen an example with SLDV and RTES for Simulink models. And those techniques are based on solvers in model checking. AI, what role can AI play? Meta-heuristic search, we've seen examples, is very useful because test automation problem can be expressed into search problems or stochastic optimization problem, if you prefer. Machine learning is very useful because it helps first better guide search. We have seen an example of that, but also learn model assumptions or approximate models for scalability. When I talked about system identification, many system identification techniques are based on machine learning, not all, and natural language processing for requirements-driven testing, which is a very important activity in cyber physical systems. Search-based solutions are useful because they tend to be versatile, to be adaptable to many environments and many testing problems. Often they help relax assumptions compared to exact approaches, even though they are heuristics, and decrease modeling requirement, and they are scalable. For example, genetic algorithms are very easy to parallelize on a high-performance computer with many cores. The drawback, though, of those techniques is that they require massive empirical studies for validation. And search, as we have seen, is rarely sufficient by itself. So we need multidisciplinary approaches that combine search with machine learning. Solvers, I've shown you only one example with constraint programming, but I have other examples with SMT and statistical approaches, and system and environment modeling and simulation, obviously. And that's the only way we can find actually solutions that work in practice to solve industrial problems. So, and when solving those problems, we need to strike a balance in terms of scalability, practicability, applicability, and at the same time offering the maximum level of dependability guarantees. So we need more of that type of multidisciplinary research. In most industrial contexts, it's illusory to believe you're going to provide absolute guarantees. So usually you need to find the best trade-off between the cost and the level of guarantee. And of course, that best trade-off is context dependent. Depend on the system, what it does, the risks involved. So that type of research cannot be oblivious to context, such as application domain. So thank you very much. There are references regarding the 3 phases of testing that I will share my slides. Thank you.
Okay.
Thank you so much.
Thank you so much. So is there any questions in the Zoom chat? Not yet. So maybe I can start with a question regarding your work about ADAS, Advanced Automotive Driver Assistant. So it's not, I would like to know if you do some check to verify that the genetic operators you apply, they do not generate infeasible test cases, infeasible executions.
Yes. We make sure of that, or at least we make sure that they are rare and can be discarded. Okay. It doesn't affect the search. Yes.
Okay, that's great. And I have another question regarding the scalability work. If you can tell us more about the fitness function, because you also mentioned use a search-based approach. So what is the fitness function?
It's based on a function, but you can guess that it's intuitive. It's based on a function of the difference between the completion time and the deadline. But it's not just the difference between the two, because it's complicated to explain, but we don't want many good runs where there are no deadline misses to obfuscate a few rare cases where you have deadline misses. So we give more weight to deadline misses when we search. So it's not just the difference between completion time and deadline, it's a function. It's an exponential function of the difference. It's described in the paper.
Okay, thank you so much. Okay, we have a question from the Zoom chat. There is Gary Levens asking what is the importance of having humans in the loop for guiding the artificial intelligence or learning process?
Normally, you want to minimize, of course, the human in the loop. I mean, for obvious practical reasons. For hardware in the loop testing, it's not possible because they need to intervene to set up the environment often to run a test case. Though in the work that I've briefly mentioned based on in-orbit testing, we try to minimize that. What we do is that we order the test cases in such a way that the preparation time to run a test case is minimized, so that the post condition of a test case satisfies the precondition of another test case, if you will. But usually it's not fully avoidable with hill testing. With respect to meal testing and seal testing, we try to avoid the human in the loop entirely.
Okay, yeah, this is the goal of
because we try to run as many test cases as possible, and so.
Okay, we have another question from Violet. We all know that the test for autonomous driving system might be endless, and the addition of artificial intelligence is to deal with the infinite possibilities. So the question is, can we generate and test more possible scenarios under limited input condition by using artificial intelligence plus cyber-physical systems?
Yes, actually, this is exactly what we did. Yes, the role of search and machine learning, for example, in that, the first example I presented, second example, I mean, I know this is an abstraction, but imagine this is a search space. Imagine this is very large, at hundreds of dimensions, okay? And which is usually the case, especially with input signals. So we use search and machine learning in order to guide the search for safety violations. That's exactly what we do. Search is obvious for certain reasons. We try to maximize a fitness function that tells us to which degree we have violated the safety requirement. And at the same time, we use machine learning in order to help focus the search on the most critical parts of the input space. So here we use two artificial intelligence techniques to do exactly what you said. And in addition, what we do is that we try to learn to characterize critical input regions. Because this is useful, because it tells, usually those systems always have limitations. They're always scenarios that they cannot handle. It's unavoidable. First, there are limitations of limitations in the hardware, in the sensors, in the cameras. So, so if they can identify this type of conditions under which the system fails or violate safety requirements, then they can decide whether or not the risk is acceptable, or whether they need to improve the hardware, and then the car will be more expensive, or they need somehow to, I don't know, repair something in their control and decision algorithms.
Okay, thank you.
So what is the benefit? Actually, I have a question. If
yes.
not So let me ask the question. So what is the benefit of automated testing, like the traditional testing over the AI based testing? Is there any difference, such as any benefit or any difference which we will be instantly seeing as an industry people?
I don't know what you mean by standard testing. What we are trying to do here is automate standard mill, seal, and hill testing. But we are just trying to automate it. Okay? So it depends on what you mean by standard testing. But we are trying to automate standard mill, seal, and hill testing.
Okay, fine.
But we are just trying to automate, that's all.
Okay, that benefit is we will be seeing like after doing or adapting the process and all, right?
Sorry. Get back to
the AI based testing which you have implemented or you have researched or you have gone through the process and all. So after implementing the AI based testing, we will be seeing the effect and all, right? Means now currently we are doing some traditional automated testing, like we are using Selenium, Java, and other kind of.
But that Selenium and Selenium doesn't solve all the problems I've mentioned. It doesn't address that. Yeah. So you know, here you have the slide I'm showing now is basically what people do, and we are trying to automate that. Okay, basically. In various ways. And I've given examples. Of course, I was not exhaustive, but that's what we are trying to address. Automate what's on the slide I'm showing currently.
Yeah. Okay.
Okay, fine.
And of course, the focus of my presentation today was to show the role of AI. And by AI, you have seen, I mean, meta-heuristic search or stochastic optimization, machine learning, and natural language processing. And also show that, of course, the AI alone was not sufficient. It needed to be combined with other things. That the solutions are always multidisciplinary.
Okay, so we have time for one more question from Eric. If you can mute yourself, maybe you can ask by yourself.
Okay, so my question basically is that sometimes when you use machine learning, you don't have enough data so that the model is not very good. If you train facial recognition with only Caucasian people, it won't work good for Asians, for example. So have you encountered this problem, and how did you tackle that?
Yes, well, okay. First, in mill testing and seal testing, we simulate the environment. So we can generate a lot of more scenarios. Not as many test cases as in testing a web system, but we can, you know, there is no human in the loop, to come back to the first question, okay? And also you will notice that many of the techniques I've presented are incremental. That is, they refine in a stepwise manner. And they have, actually I haven't gone into the details, but they have smart sampling strategy to know what test cases to sample to be more efficient. So if I take an example, which would be the best example based on my slides, but let me go back to yes, for example, in ISSTA, which was actually presented at ICSI last week. You can see here there is an iteration where we refine the surrogate model in a iterative manner, and at every iteration we generate in a smart way. I cannot go into details here, but additional test cases to refine the surrogate model. And in the previous technique that I also presented here, this is also iterative, where we keep running more scenarios in certain critical parts of the input space in order to iteratively refine our understanding of what characterizes a critical scenario, and in order to increase our chances by generating test scenarios in critical parts of the input space. So it's all iterative. We build those decision trees iteratively. We keep regularly, as we add more test cases, refining the decision trees. Okay.
But are you sort of, and you also mentioned that you do run a large search in a big input space. But are you sure you have the right input space? I mean, I know it's big, but
okay, but here the input space, well, it depends on the context here. But here, I don't have a slide. I don't think so. I didn't keep that slide. But here, the input space is characterized by a domain model that characterizes everything that can change in the environment. So, of course, what can change in the environment when you use a simulator is determined by the simulator. But for example, the simulator has different road topologies, weather conditions. And this is what, in that example here, okay, determines the input space. And of course, there is work to be done in determining the input space. And usually in that example is determined by the simulator you are using, because usually a simulator cannot do absolutely everything. So there are limits. Now, if you do higher in the loop, then of course you are less constrained, but you can run less test cases. So.
Okay, I think it's time. Thank you, Eric. I think it's time now to move to the next talk. And please, Lionel, if you can stay with us until then, we have the panel discussion. Thank you.
All right. So, thank you.
Yeah, thank you. So the next talk is by Luca Berardinelli, and the title is Uncertainty Modeling and Evaluation for Dependable IoT Cloud System Design. So please go ahead. Thank you.
So I'm going to share my screen. Just a second. Okay, so start my presentation. Okay, can you see my screen? Hopefully, yes.
Yes, thank you.
Okay, great. So good morning, everybody. For those that are in LA, I don't know, unfortunately, we cannot do the meeting in person. So this talk, Uncertainty Modeling and Evaluation for Dependable IoT Cloud Systems Design. So this is a work done in collaboration with Onlin Tron. I think he also is in participating in this meeting. And yeah, a very short, a very short introduction about myself and my co-author, Lin. So I am a postdoctoral researcher at the Institute for Business and Software Engineering in Linz in Austria. And I'm mostly working on model-driven engineering principle and practices applied to, let's say, any complex system, and in particular to cyber-physical systems, production systems, you know, or also in the automotive domain, a bit also on smart cities. And recently, we're also working on low-code platform and DevOps. My colleagues and co-author is Lin, is associate professor at the Department of Computer Science at Aalto University in Finland. And together we work on this topic since, in particular, since a couple, 3-4 years, because we worked together in a Horizon 2020 project that was called U-Test, Uncertainty and Test Under Uncertainty. And in this talk, we are basically summing up the outcomes, a little bit the outcomes from this project and how we are further developing the outcome from this project. So first of all, a very brief outline of the talk. So at the beginning, I will try to introduce in particular about what are IoT cloud systems, even though probably is even not necessary due to the audience here. Then I will introduce a bit the concept about model-driven engineering and DevOps, and then some topics, some discussion about what is uncertainty and how we can combine it with IoT cloud systems and model-driven engineering. Then we will show our solution for uncertainty model evaluation for dependable IoT cloud systems. And in particular, we focus on development side, let's say on design of uncertainty. And then also we will show how recent work on how to move from dev development time to simulation time, operation time via edge as code simulation. Work done by author Lin Zhuang. Then we will conclude our discussion and talk. Okay, background. First of all, okay, what is a cyber-physical system? Well, it's a combination of software, hardware part with the environment and also humans. And in particular, in this talk, we are concentrating on the infrastructural part of cyber-physical systems. What does it mean? It means that we are concentrating on designing and simulating and deploying some typical units that you can find in the infrastructure description of cyber-physical systems. In this case, we are considering the IoT elements, cloud services, edge nodes, and also details about the network. And yeah, and in particular, what we want to stress here is that all these elements that belong to CPS infrastructure can be basically developed by a developer. So basically, you have a full control of it, or part of the system can be provided by a provider. Indeed. So, and what does it mean? It means that probably at least the control, your own control on this provided part of the system is not complete. Well, on this slide here, let's try to figure out what I mean for based systems. So you can see here in the picture how to describe a scenario in our case. So we have a developer
Luca.
and a provider. Yes.
Yeah. If you can remove the video because the connection is not very clear. Maybe you can remove the video of yourself and just leave the screen sharing. Thank you.
Okay. Great. Okay. So I hope now it's better. And yeah. So what I'm trying to say here is that basically this is in this picture we describing an engineering scenario where we have two different stakeholders that usually interact among them. So they are developer and the providers. And developers build from scratch or directly own the software and the physical units of an IoT cloud systems, sensor, actuators, gateway, edge elements, like message brokers, for example. And they can directly manage network functions like firewalls, routing algorithms, bandwidth, and they basically a developer can implement ad hoc services, and basically they own the knowledge, they own the data management platform, they own the system in this case. And then, as I said before, if a developer owns or has directly developed the software and physical unit of an IoT cloud system, we can assume that she has the full control over it during the whole life cycle of the system. At the same time, we may have some infrastructure units that can be maybe not directly developed for whatever reason, maybe for economic convenience or lack of expertise by developers. So in this case, the same infrastructural elements can then be provided by an external provider. Here we are not discussing at which extent on how to choose the right provider for a given infrastructural element. Okay, so here in this talk we can for sure say that if you are not developing the platform, you basically don't have you may lose the full control over it, and you need to try to cope with this. Okay, and here is just an example of an IoT cloud systems taken from the reference you see here below. This is a scenario for a port, where a port control service is monitoring the arrival and the paths of vessels and trucks via gates, and which alarms generated by different events. In these and similar scenarios, we can imagine that interaction, there is a lot of interaction and coordination among a large number of infrastructural elements. And the typical challenge here is dealing with, with this complex system and considering different execution scenarios and how to do that both at this time and on the operation time. Yeah, and here basically how we can deal with the complexity and how we can with let's say activities that we have to carry out at development time and at operation time. Okay, so basically I can introduce the concept of model-driven engineering DevOps. So for model-driven engineering, basically it can be defined as a methodology for applying the advantages of modeling throughout the whole engineering software lifecycle. And basically we can say that the model is the result of models transformation. So, and the goal is to automate as much as possible each step of the engineering. On the left side, on the right side of the slides, you can see a definition of DevOps that is taken from this reference here below. That is about a literature review on definition of DevOps, and the DevOps here is defined as a methodology aimed at bridging the gap between the dev and ops time, emphasizing communication, collaboration, and continuous integration. Also the delivery and with the automated deployment, So you can see there is a lot of the goal of our goal is trying to let's say to combine these two words, and in particular you can imagine that generic let's say engineering steps that here depicted as a transformation task on the left side maybe can be repeated many times through a DevOps process during for code generation, or to generate build scripts, to generate test cases, or even to generate analysis model and basically carry out some non-functional analysis of the system under development. And of course, it can be the same models can be used at the same time, maybe for generate execution traces that can be used later on to close the loop and read these execution traces to upload, to update the original design model. So the goal here is to combine the two things together. Finally, uncertainty. So uncertainty, there is an ongoing effort, the object management group called Uncertainty Modeling. It is a research proposal. And basically, there is the goal is to find a way to present uncertainty in the most general sense. And the definition here is taken from the reference you see on this slide, and based on this paper that was also contributed in the UTest project, is that uncertainty is basically defined as a lack of uncertainty and lack of knowledge about the timing and the nature of the data you're using, the system, the future outcome, and so on. So basically, if you want to combine uncertainty with modeling and DevOps, you can about basically you can consider the model as a source of your knowledge. So basically here on the left side, on the right side of the slide, you see a set of concepts and relationships. This is called meta model about that define how to model uncertainty. And uncertainty is considered let's say a subjective phenomenon. No? So basically, there is a belief agent that owns some belief statement about a reality of interest. In our case, we can consider a model as our belief agent that and its its modeling elements out as the belief statements. And then basically, depending on the degree of, let's say, trust we have on the model, then we can define the uncertainty of our model. So how to combine uncertainty with IoT cloud systems? As I said before, IoT cloud systems are complex. The development process can move from model in the loop, as we have seen before, through software in the loop to out in the loop. Of course, there is multi-parties operate, and in general, it is intrinsic to engineering activity, and you can, for example, based on the definition given by this paper, by this work on uncertainty, you can think that the uncertainty is higher when there are many belief agents involved. So in our case, we have developers and providers involved that they can generate produce different models of the systems. And of course, there is the number of belief statements. Dealing with uncertainty very, very complex. So how we try to, let's say, to model uncertainty in a cyber physical system. The first goal was to extend the definition of uncertainty that was given, that was very, very general on purpose for the domain of IoT cloud systems. And for example, since we are addressing the uncertainty that can affect the infrastructural description of IoT cloud systems, we extended the model with a taxonomy, let's say, a classification of uncertainties that can affect the storage, the data delivery, the elasticity, or the actuation environment, and the governance of the structure of IoT cloud system. And here you can see also some properties that that were defined during the UTest Horizon 2020 project in order to describe uncertainty. Uncertainty is an evolving concept. So basically, it can appear or disappear, can be persistent, can be recurring, sporadic. It can basically appear at design time or runtime, deployment time. It can affect the different aspects of the system. Let's say it's a very, let's say, complex term, so it can affect performance, availability, reliability, and so on. It can be technological. It can be also due to intervention of humans and so on. So thanks to this classification, you can create a model of the uncertainty for your systems. And as soon as you have a model that is, let's say, you can use it throughout your engineering process to understand what is going on. And so basically, what we are doing here is trying to show you how we deal with uncertainty during the devs phase. So when we need to create models at design, we have models that we use for design purpose, or to generate code or configuration files and so on. And so the scope and the goal of this talk is more on the green box that you see on the left side. That is part, as I said before, to a wider scope of the UTest project, where based on models extended with uncertainty annotation, partners of the project were able to generate a set of test cases about the system under test. So let me go into detail a bit. So basically, what I'm trying to show here is how we deal with code. So when that basically in if we consider a model-driven engineering process, it means that we have to deal with models. We have to edit models. So we have to check their consistency. We have to validate this model with respect to the language, to a domain-specific language, or in this case, the unified modeling languages we are using to create these models. And so basically, in our approach, we were describing IoT cloud system using UML models that, as said before, corresponds to the beliefs we have about our system. And as soon as we have a UML model, the goal was to perform a design activity using an editor that is aware of the uncertainty we have to deal with. In order to do that, for example, we defined a process for uncertainty detection and refine of the system based on the detected uncertainty. And yeah, so in the next slides, I'll try to how you are able to edit a model, and you can customize the tool, the modeling editor in order to deal with uncertainty. So, for example, here let me focus on the modeling step. In this case, as I said before, we are creating a ML model of a cloud-based cloud system. And here we are using, for example, the open source Papyrus UML editor. And for example, here we have a cloud class diagram, also object stereotyped with cloud service stereotype, okay? And this is a usual common step. So you want to describe the structure of your system, you can use diagram, okay? And for all, let me see. As soon as we have this model, what we can do is to check a profile in the right way. We can check the profile. For example, in this case, a cloud service can be defined in terms of the cloud provider, the service type, the data provider. I mean, depending on the profile and stereotypes you are using to annotate or extend your model, you may be subject to different uncertainty. And probably I missed to tell that, but for example, one of the source of uncertainty is missing information or underdefined information. And in this case, an uncertainty can be the missing information about a profile, okay, a profile application or a stereotype application. So basically, what you can do is trying to extend your editor with validation rules that basically detect missing information, in this case, missing properties for your profile, and suggest you some fixing rules in order to improve your model, okay? And in this tool that we called Tool for Uncertainty Modeling and Evaluation, T4UME, basically we are able to generate a set of validation rules based on the profiles you apply on your model. So using the same model-driven engineering principles, so models plus transformation to generate code, software. Here we are using models and transformation to generate the validation rules that are loaded on your model editor to check to detect uncertainty, in this case caused by missing information. And here on the right side of the slide, you can see the definition of the cloud service stereotype and the code as the validation rule that has been generated using a model to text transformation. The resulting validation rules is specified using a language, the Epsilon validation language that is provided by a model management framework called Epsilon that is available in Eclipse, easily integrated with any EMF-based Eclipse modeling framework-based tool like Papyrus. since Papyrus is a modeling is a UML modeling tool, and is basically it's based on the UML meta model defined using the EMF platform by Eclipse. So we combined Epsilon and Papyrus, and we also provided some transformation to generate these validation rules. As soon as you have this validation, basically it's, you imagine that you have your editor with some, you can validation button, it's available in Papyrus. And then, of course, you get some warnings or some, let's say, yes, warnings that the modeler can see and can check, and basically what kind of uncertainty, and in particular what kind of infrastructural uncertainty can be found on your model. For example, here you can see that the validation rule that have been generated is following the uncertainty, the infrastructure uncertainty meta model that was presented in slides before. For example, there we have uncertainty about data delivery, actuation uncertainty, elasticity uncertainty, and so the goal of the validation rule is to provide a fixed routine, a fixed function that is able to change your model based on the detected uncertainty. Now the question is, what kind of fix or what kind of refactorings you can apply in your model? Well, it depends on the engineering phase, and it depends on. In our case, it was based on the fix. The refactoring was required in order to generate test cases. And based on common model-based testing approaches, usually you have to enrich your model with state machines, okay, in order to generate test cases. So, for example, here you can see that a fixed rule, the fix for that detected the missing information about cloud provider is generating let's say a minimal state machine for your model, okay, and see the result. So as soon as the modeler or the developer, the designer detect the uncertainty, then it can apply the fix, and some additional pieces of your model can be generated. And in our case, for the sake of the project you test, we were generating some state machines. Yeah, so then you can imagine that this step, let me go back to this slide here. You can imagine that this iteration on generating rules based on the profiles you want on the model, the detection and the refactoring steps, repeat many times. At each step, you can improve your model. And at each, as many iterations you carry out, basically the goal is to reduce the uncertainty, because you are enriching the model with, we are removing the missing information problem, and you're adding additional information on your model. And as soon as you have a satisfactory UML model that contains all the need for the particular design step, for example, you can you may need to generate some configuration files for your platform. Usually, there are any configuration files for RT cloud architectural elements are given in JSON. So one possible step, as soon as you have a very detailed UML design model, is to generate some JSON files out of it. And this is again done using creating the two-type transformation. In this case, in this slide, you can see, for example, a virtual sensor, an electricity sensor was transformed into a JSON specific. Here I'm skipping a lot of details that are more, let's say, interesting for model-driven engineering experts, because here, for example, you are generating JSON files is not so straightforward as you can imagine, and you can see details on the GitHub project how in order to know how it's done. And as soon as you have the JSON file, basically you are somehow, let's say, complete. I mean, you are completing the design process, at least for us. And what is the other part of the work is about let's say how to support uncertainty at operation. Of course, we are still a huge gap to cover and to fill in, no, beside the design phase and the operation phase. But in this case, these two work were done in parallel. On the development side, we were using model and generating different artifacts at the same time. Of course, there was a work done in particular by my colleagues concerning automation, how to support simulation at operation time. So basically, here you can see the goal, and the goal was to deploy IoT cloud-based systems that is a mix of real running components and basically it's very close to the concept introduced in the talk before, where basically we need to move from model in the loop to hardware in the loop. No, so basically we want to step by step we want to remove simulated components and replace them with big ones. Of course,
sorry,
Luca,
be done. If you can wrap up, please. We are.
Oh, sorry, I'm late. Yes. Okay. So yeah. So this was the second last slide. So, and here you can see that while repeating the iteration loop, you are moving from abstract platform. You are and basically you are somehow you can also reduce the uncertainty in your system. Okay. Next. Very briefly, of course, very quickly. We are working on twin. So basically, the very close combination of models at the same time around time can be considered part of the work done in the digital in the executable semantics to models so that you can close the gap between devs and runtimes. And yeah, this can be done using standards like functional mockup interface for continuous simulation or executable meta object facility execution platform. Yeah, sorry for being a bit late, but I think it's
okay. Thank you. Yeah. Thank you so much. And I think we have time for a few questions. Is there any question from the chat? No? Okay, so maybe I can ask you one question about what kind of a subject you use in your experiment. Can you give us more information about that?
Sorry, what do you mean?
Yeah, what kind of a subject you use for running your evaluation? What kind of IoT systems?
Okay, yeah. Well, basically there were a couple, two industrial case studies that came from the UTest project. So, and they are documented in the references given in this presentation, and they were about a sport. I think it was monitoring the health of hockey players. One of them. So we have some sensors applied on hockey players, And there was also another use case in I think it was a lab scale production systems with a conveyor and moving elements from place A to place B and so on. So, but so the industrial use cases are documented in the deliverable, the UTest Horizon 20 project, and the approach is exactly this one for modeling uncertainty.
Okay.
The other case studies are available in the IoT Cloud Samples publication by Trong, by my co-author.
Okay, so we have one more question from Hao Yun. Is asking whether can UME give fix a suggestion for existing components? Is there any suggestion to refactor existing components with the minimal change?
The fix phase, it's really, I would say, system dependent. I mean, it really depends on the system understanding you have, no? And it can be as easy as generating a string, or can be complex as generating, state machines, very complex state machines. So it's up to you, and also depends on the modeling language you are using. So it's up to you to implement the fix rule. So there is not a single answer to this. So maybe yes, you can do whatever you want, but there are no predefined solution for fixing problems.
Okay, thank you. Okay, if there are no any other questions, we can have a break. As I mentioned before, one of the talk will not be done today, so I think we can have a 15 minutes break. So we can start at 6 p.m. UCT time for the third talk, and then we will have the panel discussion. Thank you, everyone.